Okay, very good morning to all of you. See, the course on ship resistance and propulsion uh, is being now offered now, and ship resistance and propulsion, that's a resistance component and propulsion component go hand in hand. Often it's very difficult to bifurcate these two topics for a ship, because when you say the propulsion characteristics of a ship is largely depending on the resistance offered by the ship at the desired speed or desired point of operation. When you say it's in any sense, it's this resistance and propulsion part cannot be, it's better not separate totally from one from the other, because the resistance of the ship naturally increase when the propeller is put to operation, which you will be studying more when you discuss about the ship propeller interaction. And also the resistance of the ship increases or it depends on the form of the vessel, and the flow to the propeller also depends on the form of the vessel, that is if you consider the fineness of the vessel and position of propeller and all that. So generally these two topics, propulsion and resistance, go hand in hand. So here I will be covering the resistance part of it, and the propulsion part will be covered by Professor Ananda Subramaniam. So the topics which are being covered under this topic, that under this course coming under ship resistance, or we will be dealing with the components of resistance, where we will be dealing with frictional resistance, wave resistance, effect of bulbous bow, dimension analysis, that is primarily dealing with the model test of ships to ascertain the resistance characteristics of the vessel. Then ship model test and resistance data presentation, that is how the model tests are carried out, how the data obtained from the model test are consolidated and presented for future design aspects, and how do you extrapolate from the model to the ship, and what are the discrepancies associated with this extrapolation from model to ship. The different methods under this being covered, like Telfer's method, Hughes method, Prohaska's method, ITTC method, and naturally you have variation in resistance when the ship moves from deep water to shallow water, and that too if the restrictions are more in the breadthwise direction, that is the case where the ship moves into a canal or maybe into a river, where you have additional restrictions coming from the breadthwise direction of the waterway. So this increases the resistance, and naturally when you discuss or when you try to find out the resistance of the vessel operating in inland waterways, where we have the three major inland waterways which inland water number 1, 2 and 3. So where ships, once the Hooghly river, then Brahmaputra and another in Kerala. So these are three national waterways, and there are a lot of vessels operating in this region, and whenever you design a ship or vessel which operates in this region of the waterway, naturally you have to consider the additional resistance or increase in resistance due to the restrictions of the waterway. So that is also being looked into as part of the course. Then this methodical series, there are different resistance data which has been evolved by performing model test conducted systematically by different agencies and put into a ready to use format, which will be useful for a person or for a designer at the early stages of design, and naturally which should be ascertained, which should be checked at a later stage when the design is finalized through a model test. then we look into all these things what we discuss, generally confining only to the conventional form of ships, mainly to the displacement type of vessels, like general cargo ship, tankers, bulk carriers, container ships, so all these come under this class. So whenever you deviate from the displacement type or conventional type, then naturally you have higher or more hybrid forms of ships and also more advanced type of marine vehicles such as planing crafts, hydrofoil crafts, then so multi-hull vessels and all that, then naturally that aspects, that type of ships need to be dealt separately. You may have to perform the calculations on the basics to ascertain the power of the vessel. So these are things which are being envisaged under this topic. The reference put forward here are the Principles of Naval Architecture edited by Lewis, volume number 3, which deals with the resistance and propulsion. Then Resistance and Propulsion of Ships, written by Howald. Then Introduction to Naval Architecture by Tupper. So these are the, you have many other books which cover the topics under ship resistance. So when you look to the what are the reasons for, what do you mean by resistance? That is the ship here which we deal with generally with the surface ship, that is a ship which is operating as a free surface, that is the interface between atmosphere and water. So the ship which is moving at the free surface is exposed to two media, one is air and other one is water. So when the ship moves forward, there will be a resistance or opposing force, a force opposing the motion of the vessel due to various physical reasons. So this opposing force is termed as the resistance of the ship. And as I said before, there are different physical reasons for the creation of a force opposing the motion of the ship, and normally it is studied during the steady speed of the ship. That is, if you design a ship for 15 knots, so you assume that ship is not in the acceleration phase, it is in the steady phase. So the resistance generally is dealing with steady phase or steady speed condition, and acceleration effects are generally ignored in this case. So the first component is you see the frictional component. You can see that the frictional component, friction, it is a consequence of viscosity. When the fluid friction is basically due to the viscous property of fluid, and due to the viscosity there will be a shearing effect between the layers of fluid, and there is a shearing effect between the body surface and the fluid. There is a relative motion between the body surface and fluid. When the ship is moving with the speed, you say 15 knots, that means you consider there is a flow opposing it or moving in the opposite direction with the same speed. This is a relative concept which you can assume. So naturally there is a flow, as if you consider there is a ship which is stationary and the flow is coming across it with the same speed, isn't it? So instead of considering a ship moving through a still water, you can also assume. So there is a flow velocity of the same speed as that of the ship. So when it comes to the boundary of the ship, naturally there is a shearing effect, and this shearing effect leads to the tangential stresses, and if you integrate the tangential stresses over the wetted surface of the body, you get the total resistance force offered due to the friction. So that is a basic reason behind it. And here whenever you talk about resistance, it is associated with basically the loss of energy occurring to the ship mainly. So the loss of energy here, whenever there is a friction, there will be the energy associated with friction is heat energy. So due to the, isn't it, whenever there is a friction there will be heat energy, even in fluid also you have the same thing. So when there is a heat energy, that so much energy is being lost to the ship, so which attributes to the resistance of the ship, which accounts for the frictional resistance of the ship. So next component is the you call it residuary resistance. Here you have the residuary resistance here. Residuary, naturally it is leftover, basically residuary. What do you mean by that? That is, if we consider the total resistance of the ship in still water, here we are not dealing with ocean waves, we are just considering still water. the ship is moving through that. When the ship moves through that still water, first thing what you have discussed is it will have a frictional resistance offered to the motion of the ship, and next thing is there will be, you must have noticed that waves are generated around it, and plus there are other components which we will see later. So, the total resistance minus the frictional resistance component, you call it a residuary resistance, and in residuary resistance the wave making part is the predominant one, that is the wave making is the major component which contribute to the residuary resistance of the vessel. Next you have the viscous resistance, resistance due to viscous effect. As I already said, the frictional resistance is one of the component due to the viscous property of the fluid. Then we will see later there are some more components which adds to it due to the viscous property of the fluid. So, all these components put together we call it a viscous resistance. Later we see in a diagram how these components are classified. So, the pressure resistance here, resistance of the normal, because you know the pressure acts normal to the surface, hydrodynamic pressure or even hydrostatic pressure, it acts normal to the surface of the body, and which you can resolve that one across the direction, that is in the transverse direction of the ship, and another one in the longitudinal direction of the vessel. So, when you consider the ship surface, you can maybe I better explain using a board. So, if you consider the ship moving, then you know the pressure acting it is normal to the surface. See here it's the normal is going to be in this direction, you have pressure in this direction. So, similarly you have pressure so this is a pressure acting. So, if you resolve this component, ship you know it's symmetric about the center line. If you resolve this component, you get two components in this way, and similarly at the symmetric point of here you get resolve these two components. So, the pressure which acts normal to the surface of the ship can be resolved into the one component along the ship and one component without ship, or called as the transverse direction. You can do the same for all the components here. So, here you can see this point you get another component in this direction, you get another one here. So, here it will be in this direction, and here you have this. So, now you consider the pressure, what happens to the pressure, these two, this symmetric. So, this pressure magnitude they are same, and these components, these two components are same, isn't it, same pressure. So, these two but they are opposite. So, what happens to the resultant of these two components, it will get cancelled each other, these two components get cancelled each other. Now, you consider a point here and a point here, you have a component in this direction, you have another component, the component coming from this point in the opposing direction. These two components get cancel each other, but these two components may not get cancel each other, because these two are, it is not symmetric about this point, this line. So, that means if you do the estimation by resolving it into longitudinal and transverse directions, you will find that the transverse components are getting cancelled each other due to the symmetry of the ship about the center line, but the longitudinal components will not cancel each other. There will be a resultant component which will act in the longitudinal direction, and if this component is along the flow direction or opposing the ship motion, ship direction, ship velocity, it adds to the resistance of the vessel. So, that is what is called the pressure resistance. So, what you call pressure resistance is coming from that. Then next component is the viscous pressure resistance. viscous viscous pressure resistance here. So, this is due to the viscous property. When there is the viscosity is there, you know there will be a formation of boundary layer around the body. There will be a formation of boundary layer around the body, and the boundary layer grow from the forward side of the ship to the aft end of the ship. So, if you consider if you have a boundary layer, so the boundary layer is 0 thickness at this point, it increases towards the aft. It goes like this. So, the boundary layer of course is enlarged thickness for here. So, the boundary layer increases. So, beyond a stage the boundary layer separates. Boundary layer won't be able to follow. You know what is the definition of boundary layer? The boundary layer is defined as, if you take a profile here, velocity profile across this boundary, you see this is a profile. That is, it is actually a fictitious line which is drawn. That is the velocity. If you consider the vessel is at 0 speed and you are having a flow at free stream flow of say u infinity, or usually you say or is equal to the ship speed. So, the free stream, the flow velocity is same as the speed of the ship, but here you consider ship is stationary, as good as the flow is in this direction. The flow here will have the same speed as this, but what is the flow adjacent to the body? The flow adjacent to the body will take the velocity of the body. Now, we are considering the body which is a ship is stationary and fluid flowing across it. So, naturally the flow velocity adjacent to the body, you will have a 0 velocity, that is why you have a 0 velocity here, but away from the body it will have the free stream velocity. So, here you have the free stream velocity and here it will have a 0 velocity. So, there is a variation from 0 to free stream velocity. So, which is usually a parabolic distribution of velocity. So, at some point you want to identify a point where which is equal to 0.99% of u infinity. You consider a point 99% of u infinity, which is as good as saying it is u infinity. So, you want to identify a boundary where this viscous effect is there and beyond which the viscous effect is not significant. So, you consider this. So, you do the same thing for different region, you get the 99% points, then you join this 99% point, that is called the boundary layer. So, this is the boundary layer for the ship. So, this boundary layer when reaches beyond a limit, it you know it goes like this and finally it may have a reverse gradient, negative gradient. So, that is a point where the flow separates. Flow is not separates means it is not following the contour of the body, it separates from that. When the flow separates, what happens? There will be formation of eddies. When the flow separates, eddies are formed. So, you consider these two cases. This is a case where we have not considered viscosity, and now this is the case where we considered viscosity, and due to the flow separation there will be a formation of eddies. When the eddies are formed, what happens to that means the flow has attained a velocity. So, when you consider this case where you consider potential flow means there is no viscosity. What do you call this point? These 2 points are called stagnation points. Stagnation points means that is a point where the velocity is 0. So, that means if you look to the Bernoulli's equation, the pressure is maximum. So, these are the 2 points, the pressure is maximum, and you know the stagnation pressure is given by half rho v square, isn't it? That is the stagnation pressure. So, this stagnation pressure, now you consider this case with this, here the velocity is 0, pressure is maximum, and that means this component will have a higher value. What is this component? This is a component which supports the ship, isn't it, which is pushing the ship forward, and this is a component which is opposing the ship. So you prefer to have this component dominating, so the resistance will be less. Now you consider this case where you consider boundary layer, viscous fluid, there is a flow separation, the velocity of flow is not 0, it is a non-zero quantity. So what happens to pressure compared to these two? The pressure here will be less because the fluid has attained a velocity due to the flow separation. So when the velocity is there, the pressure drops. When the pressure drops, what happens to this component? This component reduces. So that means effectively this component is more dominant, it will increase the opposing force, which is a resistance increases. So you clearly understand what is viscous pressure drag or pressure resistance. When viscosity is present, a boundary layer is formed, the boundary layer builds up from the forend of the vessel to the aft of the vessel. The boundary layer thickness is higher in the aft of region of the vessel, and in the aft region, when the boundary layer thickness increases beyond a limit, naturally there will be a separation of flow, flow separates. When flow separates, eddies are formed. When eddies are formed, the velocity is not 0, that means compared to the potential flow case, the pressure drops. When the pressure drops, the assisting force of the ship reduces, that means the opposing force coming from the forend due to the pressure increases. So which obviously means the resistance of the ship increases due to the viscous effect. So that is the contribution on the resistance of the ship coming from the viscous property, or the term which you say is a viscous pressure drag, pressure resistance. Then you have the wave making resistance. Well, wave making resistance, again here it is, as I said before, it is not dealing with any ocean wave, it is still we are considering still water. You must have noticed that ships moving through still water, they generate waves due to change in pressure basically when it moves. Actually you consider it as a pressure point moving, and it has a characteristic wave pattern and appearance and all that, which we will see later. This wave, the waves which are created, now we are discussing only about surface shapes. When the waves created at the surface of a, or in the surface of between atmosphere and water, that is called the free surface, we call it generally free surface waves. The waves at what you see in ocean, or generally the waves created by ships and all that, free surface waves, because they appear at the free surface, that is the interface between air and water. So these are also called gravity waves. Often the waves which appear at the free surface are also termed as gravity waves. The reason for that is water is treated strictly as an incompressible fluid. That means the volume of water is not getting reduced by application of pressure, that is called, even if you compress it, it is not getting compressed, even if you apply pressure it is not getting compressed, volume remains same, that is why you call it an incompressible. So now you consider there is a force disturbance, you just consider case of a stone being dropped. So when you drop a stone, due to there is a change in momentum when it enters the water, and that results in the force pushing the water column down. So when you consider a stone and you consider free surface, this is coming down, and when it comes here, the water column here is being pushed down. So what happens to the adjacent water column? Water is incompressible, so even if when you apply pressure, its volume is not reducing. So what happens to the adjacent layer of the water? It will come up. Here also it will push up the water column adjacent to it. So it moves up, the water column moves up, but it cannot move up indefinitely. The reason is why the water column cannot move up. Gravity acts, because water particle possess mass, the gravity acts on that. Because of the action of gravity, the water column adjacent to that, which is moved up, is being pulled down. When it is being pulled down, what happens that, so this has moved up, when it is being pulled down, it same thing is repeated here also, the same thing is repeated, it pushes the next column down. So what happens at this column, it emerges out. So this will go on like this. So that is how waves are created. Consider still water, stone is dropped, because of the application of pressure or force, the water column is being pushed down, and water being incompressible, the adjacent layer emerges out, but gravity acts on that, again it is pulled down, then the subsequent layer moves down, and this keep on repeating, and you get the waves. So due to the action of gravity on the formation of wave, it is also called gravity waves. So waves are generated when the ship is moving through water, and you know that compared to still water, the wave so you consider water particle here and water particle, now due to the action wave, the water particle has moved up. So water particle possesses mass, when that mass is lifted, what happens, what type of energy is associated with that, it has got potential energy, isn't it. So due to the, that is wave now got a potential energy, and you know that the water particle inside a wave will have a orbital motion. With the deep water you have a circular orbit, again this water particle mass is moving with the mean position remains same, deep water, but the water particle possesses, it's subject to a rotational motion. So mass and is moving with a constant velocity, then what happens, what is the energy associated with that, kinetic energy, half m square. So you have rho g h coming from the, or mgh basically, isn't it. You have the potential energy, and then you have the kinetic. So the wave, any wave you see in ocean, on water surface, you see that it is associated with energy, which is being contributed by potential and kinetic. Potential by virtue of its movement, vertical position, and kinetic due to the orbital motion of the water particle in the wave. So the total energy, the wave possesses an energy. From where does it come from energy? Ship is moving, you consider still water, ship is not moving, still there is no wave. Now still water, ship is moving, it is creating wave, and these waves possess energy. Okay, and where law of conservation of energy applies now, isn't it? Energy is not created, not destroyed, so it is a converting from one to another, isn't it? If you take a system, there should be a constant energy, isn't it? So here that means the formation of wave, and the wave possesses energy, and this energy is being supplied by the ship, which results in loss of energy to the ship, and hence that component is called the wave making resistance of the ship. So that is the wave making resistance of a ship. So that is one of the major component, and you know that the wave size created by the vessel depends on its speed. You just consider any ship at low speed, the wave making is less, at higher speed the wave making become higher, and naturally the component, wave making component of the vessel will be higher at higher speed. We see the relations later, how it is related to the speed of the vessel. The next one is a wave breaking resistance. You can see here wave breaking resistance. When the ship is moving, okay, I will just draw it here. You just consider ship moving in this direction, which is floating at this water line, here there will be a wave formed like this. We will see the components of waves later. Waves are formed. Here, what is this point? What is the velocity at this point? 0. That is a stagnation point. What is the pressure? Maximum. So naturally, there will be elevation of water due to the pressure. So the bow part of the ship will have a wave crust formed. That is, the bow of the ship will form a wave with a crust beginning, and then it propagates towards the aft. So this is called the bow wave. This is the bow part of the ship, and this is called the bow wave. And if this go beyond the limit, what happens? If this height increases, height of the wave increases, or in other terms you say it's the steepness of the wave increases. For the same length, the height increases, wave steepness increases, and if the wave steepness go beyond the limit, what happens? The wave breaks. When wave breaks, what happens? There will be formation of eddies, or breaking of the wave results in more water particle kinematics. So that means there will be more energy associated with the breaking of the wave. And from where does this energy come from? From the ship. So breaking of wave, bow wave, leads to an additional resistance. And actually this component is quite small compared to frictional and wave making component, but still there is a increase in resistance due to the breaking of a wave. So what you do is, whenever you design a ship, if you can take care that the breaking of wave is avoided, then you are reducing the resistance, that component of it. So care is always taken to reduce that component. Even a small saving in the resistance of the ship matters a lot, because the ship is designed for a period of 25 to 35 years of operation. When a small saving, 2%, 5% saving in resistance matters, because there is so much fuel saving, and fuel cost over a period. It's a recurring expense. Naturally, that will turn to be advantageous for the ship, and now the IMO is giving more importance for reduction in resistance. They are talking about green ship. So that means when the resistance comes down, the emission also comes down. So it's more eco-friendly, and naturally, which they call it a green ship. So you have to adopt different methods, maybe improving the efficiency of the engine used, or maybe improving the propulsion efficiency, or reducing the resistance. All this matters in the reduction of fuel consumption, and subsequently on the emission, which will give a much better eco-friendly ship. So even it's the small thing, even though you say it's a wave breaking resistance, a very small component, maybe 5% or even less, doesn't matter if you can save maybe 2 or 3% from that part of it, or maybe 5% of that. It matters a lot for the whole range of the operation of the vessel. Other components of spray resistance. Spray resistance is the energy expended in generating spray. Normally it occurs in planing crafts. When the high speed vessels, you say a lot of sprays are coming out, and sprays results in more water particle kinematic, and subsequently the kinetic energy associated with the water particle kinematics, and naturally that energy is being spent from the ship. So due to that formation of spray, you have more resistance. That is called the spray resistance. So often in high speed vessels, in planing crafts, you see that the spray propagation is arrested, which will help in also to reduce the resistance of the vessel. So these are the general components, and other components we look into. One is appendage resistance. So ship, normally depending on that, sometimes the ship model tests are done with the bare hull alone, without the rudder, without the propeller bows, without the shaft bracket, without the bilge keel. So all these come as appendage, something external to the main hull of the ship. So all this shaft, bilge keel, rudder, everything can be treated as an appendage. So if it is not considered as part of the main hull, then you can give an allowance for the appendages, which will increase the resistance in many counts. Naturally, it will increase the wetter surface due to the appendages. So the frictional resistance will be higher, and then it will lead to, if it is close to the surface of the ship, it will have wave generation, which will again can contribute to wave making part, then whenever there is a due to the boundary layer effect and flow separation, there will be a effect due to the viscous pressure resistance, and also it can have a contribution to all various components. Generally people confine the estimations only to the frictional resistance part. So if the appendages are there, you put an extra, you find out what is the additional wetted surface coming due to the appendages, and then you put a factor for that into the S factor, and finally multiply that with the frictional resistance to get the increase in resistance due to the presence of appendages. Another thing is roughness resistance. Roughness, you know that the ship put to operation in sea will be subject to corrosion, because the steel ships generally, you know, this highly sensitive to sea water, resulting in corrosion, and corrosion results in the roughness, increases the roughness of the ship hull, and also the ship being in marine environment in water for continuously for a longer time will become a comfortable place for the many biological living beings to live on, isn't it? So like weeds, barnacles and everything, they start living on the underwater wetted region, because it's always wet and it's comfortable for these things to be there. So they get started living on the surface of the vessel. That's why it has become mandatory to dry dock the ship, that is to take the ship to dry region or shore facility, then clean the underwater, so we chip all the growth and clean the surface, underwater surface, repaint it, make it smoother again. So what happens is that due to the growth, naturally the roughness increases. When the roughness increases, what happens? The frictional resistance increases. When so naturally the ship has to spend more power to get the speed, or the speed comes down automatically due to the increased resistance. So again it's a more fuel consumption, more money for the owner, and subsequent effects, as I said, emission, things like that. So when the ship resistance is estimated, it is done using model test. Model is having very smooth surface. The resistance which you measure from the model and then extrapolating to the ship is not taking care of the roughness due to the corrosion and fouling. So when you estimate the power for the ship, naturally you have to give an allowance for these two, that is for the roughness, these two means the fouling and corrosion effects. So the roughness of a model and roughness of a ship are totally different. So the roughness increase in the case of the ship, and you have to increase the resistance estimated from the model to get an actual value for the ship which is in operation. Air resistance. The ship, you just consider still air, there is no wind, you are not considering a wind, it is still air, like what you consider still water. The ship is moving forward, so that means as good as above water portion of the ship is having a airflow in the opposite direction, isn't it? There is a airflow in the opposite direction. So this air, the structure above the water of the ship, will be subject to the resistance offered by the air, and that is considered, that is taken as the air resistance. Normally for conventional ships, the speed is less and air flow also is less, and so the component of air resistance and also the density of air, you know, that is 1/800th of water. So the density is also very low. So naturally the resistance component coming from the air resistance is quite small, and that too for a low speed ship it is very small. That is the reason you find that superstructures of this type of ship, that is structure above the water, is not so streamlined for low speed ships, whereas when it comes to high speed vessels, you streamline it because the speed is high and you know the force is proportional or resistance is proportional to velocity square. So, air resistance part, that is one you have to consider. Next one is steering resistance. Steering resistance, steering of ship is done using rudder, you know that conventionally it is done using rudder. So, for turning the ship or often to maintain the straight course for the ship, rudder is used. You know rudder, mainly for ships with a single propeller. If you consider a ship, I am taking a section of that aft view, okay, this is the waterline. You have a propeller here. Now it may be rotating in one direction, it is at center line. The flow kinematics around the aft region is not symmetric about the center line, isn't it, because it is rotating in one direction. If it is a twin screw and they have a symmetry rotation, maybe outboard or inboard rotation, you have a symmetry of kinematics. You consider a single screw vessel and you know that it can rotate in only one direction. So, there is going to be an asymmetry of the flow kinematics with reference to the center line of the ship. So, asymmetry in the fluid kinematics results in asymmetry in the pressure distribution. Asymmetry in the pressure distribution results in the resultant force generated by the propellers is slightly off the center line, because pressure is not same on either side. If the pressure is same on either side, it will act along the center line. Since the pressure is not same, then the resultant force will be slightly off the center line. If the resultant force is slightly off the center line, what happens? Suppose you consider this view. Instead of the force acting in this direction, now the force is slightly off the center line. Suppose this is a force coming from the propeller, and center of gravity, you know, is always at this side, take it as center. So, what happens? There will be a moment, isn't it? This force will result in the creation of a moment. If that moment results in what? It will turn the ship. You want the ship to go straight, you are not putting the rudder to any angle, if rudder is at 0 angle, still the ship turns, because due to the kinematical asymmetry of the propeller with the reference to the center line of the ship. So, normally what ship does is, ships with single screw, they do is they put a small rudder angle to counteract this moment, so that this moment is contracted, ship will keep a straight course. The rudder, you know that it is symmetric, and when you deflect it, it generates a force and moment. When you deflect the rudder, what happens to the resistance of this due to that deflection? You are blocking it, isn't there? Should be an increase in resistance, isn't it? So, which you call, is called the steering resistance. So, ship is steered by rudder, and rudder often is put to a small angle to counteract this asymmetry generated by a single screw vessel. So, this leads to additional resistance, which is termed as the steering resistance. Then the last one, which I have already discussed, increase in resistance increase due to waterway restrictions. Waterway restrictions leads to a lot of complications. When the ship moves from deep to shallow water, usually shallow water is rated as less than 2 times its draft. If the water depth is less than 2 times the draft of the ship, and also it is obviously is again depending on the speed. Conventionally, you say for normal ships, conventional ships, if the water depth is less than 2 times the draft of the ship, you treat it as shallow water. When the ship enters to shallow water, what happens? Suppose this is a ship, I am just saying it is a shallow water. Now the bottom is very close, so this is less than 2. So what happens? The water flowing through this part. So there will be a boundary layer formation here at the bottom. You see there is a boundary layer which grows towards aft. The bottom, which is also close to the ship, will feel the flow, and then it will also generate a boundary layer. So there is a boundary layer formation coming from the bottom of the ship and also from the waterway bottom. I have already said boundary layer, inside boundary layer the flow velocity is less. Okay. So now the water here has to escape to this side. There is no conservation of mass, it has to flow. So the same water, when it flows through, try to escape through the bottom of the ship. First thing, due to the constriction, due to reduction in waterway itself, there will be increase in flow, isn't it? The flow increases, flow velocity increases. It is obvious, you must have noticed that when there is a channel, when there is a reduction in the section, the flow increases. The law of continuity should be maintained, so the velocity increases. Same thing here, the flow velocity under the ship increases. When the flow velocity increases, what happens to pressure? Pressure drops. When the pressure drops, what happens to the buoyancy? Buoyancy reduces. So to make up the buoyancy, ship will sink more. When the ship sinks more, what happens to the wetter surface? It increases. When wetter surface increases, resistance increases, isn't it? So the resistance increases when the ship moves from deep to, it is coming from the frictional resistance part. In addition to that, when the boundary layers are formed, the bottom and also at the bottom of the waterway, that will give additional constriction to the flow, because inside the boundary layer the flow velocity is less, so the constriction is more. So compared to the flow velocity here, the flow velocity here will be more because of the boundary layer formation, because there is a constriction created by the formation of boundary layer and its increase in thickness at this region. So the flow velocity here will be more compared to this region. So what happens to the pressure compared to these two regions? Which region will have low pressure of the two? Because the flow velocity is high, the pressure here again will be lower. Then lower pressure, what happens to that? The aft region of the ship will try to sink more than the forward region. So what happens? Which we call the ship will trim. So when the ship enters from deep to shallow water, it sinks and also it trims. So both things, which you generally term as the term called scat. This is a term used to define this phenomena, that is the shallow water effect of ship. So due to the constriction, flow constrictions, these things happens. Then in addition to that, if there is a transverse restriction, suppose you consider the ship here, you are putting a boundary at the bottom and also at the side. Now the ship is moving through the canal. So you have restriction here and here. So naturally these restrictions will enhance the flow velocity and the scat effect will be more compared to the case where only the shallow water. There is shallow water, when you say, generally the transverse restriction is not considered, but if there is a transverse restriction like in canal or river, naturally this problem get aggravated and the scat effect will be higher.